In this section, we're going to play with the concept of normal distributions. Now, there's going to be four big ideas. We need to, number one, know what is a normal distribution. That's kind of important. Then we're going to talk about what the graph and the equation are of normal distributions. Then we're going to come up with a new way of referring to the normal distribution, or as the standard normal distribution, or the standard normal curve. And then finally, and it's been a little theme for the last couple sections, we're then going to figure out how the binomial looks with a normal distribution. Okay, so um, nonetheless, let's start off with what is a normal distribution or a normal curve? Well, it has certain properties. The basic understanding that we're going to need for this class is it is unimodal, meaning there is one mode, there is one mean, there is one normal, there's one average, however you want to refer to it. Okay? And so therefore, because of that, it happens to be right there. Okay? And it is symmetric about that average. So meaning if you were to draw a line down the middle and you were holding a mirror up, it would look the same on both sides. Last but not least, the outliers. Now, a statistical vocabulary word called outliers, we're not going to go into it in this class very much, but what it means is the people or the items or the whatever it is that are really, really far away from normal. So not the average height people, but the super, super, super tall or the super, super, super short. And they're allowed in normal curves. They just have to be limited and they must be balanced. So for every tall person, there's also a short person. You can't have an unbalanced number of outliers. All right, that's the big idea of normal. And so what we're saying is the average comes in the middle, and that could be any of our versions of average. It could be mean, it could be expected value, it could be any measure of central tendency that fits as long as it has these properties. Unimodal, aka one mode, single mode. It has to be symmetric about the average, symmetric about the mean, and limited but balanced outliers. Okay, that's it. And then, of course, the way that we're going to use it in here is we're going to talk about the area under the curve. That area is going to equal 100% of your population, or aka, as a decimal, 1. When you add up all the areas, it's going to equal 1. All right. So now, here's your equation of a normal distribution. Have you seen this before? Well, we know that the sigma means standard deviation, sigma squared means variance, and the mu is another way of writing mean. And again, that mean doesn't have to literally be mean. Mu can be any of our averages, just depending on context. Okay, there's the equation. Good luck typing that into your calculator. It's not going to happen. Okay, so what we're going to do instead is we're going to come up with something that's called the standard normal distribution. Okay, the standard normal, what we do is we let mu equal 0 and let sigma equal 1. And so then you get this equation that we have right here. And the nice thing is you can look up above and see where this came from. Everywhere we had a sigma equals 1. Everywhere we had, so here's our standard deviation. That was 1. Then we had our variance. That is 1 squared. Hey, so that's just 1. And now this is much easier to work with. So you could use either one. They both do the same thing. But what we're going to do instead is we are going to focus on converting problems into a standard normal curve, into a standard normal distribution, instead of this one. Because what that means is if we're doing the normal one, just the normal distribution, then what we're looking at is, well, I'll use mu, some mean, where we're going to go plus a standard deviation up, minus a standard deviation down, and every time these numbers are going to be different, they're going to be interesting, and it's all going to depend on your data set. The mean will be a different number regardless. So you could be talking about average shoe size or average test score, and the standard deviation will change with it. Okay, with the standard normal curve, it has a slightly different meaning, a slightly different idea. What we're going to do here is we're going to say, well, regardless, I'm just always going to make my mean be 0. And my standard deviation will always be up 1 or down 1. So therefore, this is a negative 1, this is a positive 1. So if I'm 2 standard deviations up or down, then I'm at negative 2 or positive 2. And that's the idea. So it makes it very, very simple to calculate and talk about. So let's work through this. Let's work through our first one. Um, let's imagine we had a test where there was an average score of 85 and the standard deviation was 12. Calculate the probability of a student scoring between a 73 and a 97. Okay, and I guess I apologize. I should state, I said it earlier, but I should explicitly state it. This represents the probability of something occurring. So it's the at that value. So you could imagine almost like this being an axis where the probability is the output, and then the or the likelihood, the frequency would be a better way of putting it. Let's refer to it as frequency. Uh, and so how likely it is for something to happen, how frequently it occurs. Okay, and then the x-axis is our standard deviations. Okay, so what we're going to do, if we're going to calculate the probability of a student scoring between a 73 and a 97, all right, so let's kind of draw what that would look like on our curve. Okay, if we were not doing the standard normal curve, we were just doing the regular one, we'd say, okay, this is an 85. Okay, and we're going to go up 1 standard deviation, which was 12, and we're going to go down 1 standard deviation. Where does that put us? Well, that would put us at what? 85 plus 12 puts us at 97, and 85 minus 12 puts us at, oh, look at that, 73. So these numbers here, specifically, they really were cherry-picked by me. Whoops, that's not a good curve. To kind of demonstrate, we could look at the curve this way, or we could say, let's call the middle 0, and what we're looking at is down 1, and we're looking at going up 1. So the area in the curve from here to here would be the same as the area in the curve from here to here if I had drawn the pictures identically. But the idea is, same idea, different representation, right? We can talk about it in standard deviations, or we could talk about it in test scores, but it's the same area. The likelihood is the same. So how do we calculate this? We're going to take this and put it in our calculator. All right, so here we go. In your y1 line, we are now going to type in this first part. So it's going to be 1 divided by the square root of 2 pi. Oops, not 2 to the pi. That would be not what I want. 2 pi. There we go. I'm going to close my parentheses. Now, the next thing I want to point out, this is e raised to the, and all of this here, this right here is all in the exponent. So in my exponent, I'm going to just type in negative x squared divided by 2, and then I'll get out of my exponent and close that off. Okay, so there's our function. Now that we have our function, we want to be able to talk about what is the likelihood. If this is the graph of the frequencies, if this is the graph of the probabilities, then what I need to do is find the area under that curve. And all of you hopefully remember from some version of calculus that you took, area on the curve is the antiderivative. All right, so we're going to antiderive this equation. No. We're going to use our calculator to help us. So what I'm going to do is I'm going to look at the graph just so we can visually see it. But you'll notice this is not a good representation. It barely looks, I mean, that's just a silly representation. So let's go to the window and think logically. All right, if our axis is going to represent standard deviations, we already know that 3 standard deviations, it covers 99.7% of the population. So if I go like, I don't know, 8 standard deviations up and 8 standard deviations down, that's going to be a pretty good curve, maybe even a little extreme. Now, my minimum, if these are my frequencies, how likely something is to occur, negative values don't make sense. So I'm going to change this to a 0. And I can't go up to a 10 because 100%, 1 would be 100%. 1 would be 100% likelihood something's going to happen. So I know where the number is, but let's just go with a 1. We're going to need to adjust that a little bit. But let's go to a 1 and hit graph and see what we see. So now, as we wait for this to go out, you're like, wow, I see the normal curve. I see the symmetry. I see the very, very, shallow outliers going on the edges, but we could have definitely picked a better number. I mean, this looks like it's not even at 0.5. So what I'm going to do is go to my y max, and I'm going to change that to a 0.5, just so it looks a little better. And we can see these things happening a little better. There we go. And playing with your number of standard deviations will make your graph look a little different. But I just picked -8 to +8 to cover everything we'd ever could run into. So now we want to find the area going from -1 to +1. So if you remember from your calculus class, you're going to, up here in the top row, we're going to go second, calculate. And option 7 was our integration button. Now our lower limit would be -1. And our upper limit would be +1. And notice I just type in the numbers and then hit enter. And wow, that's amazing. I'm going to make sure that we can see this really nice, because we already know from the rule of 68, 95, 99.7 that if you get the area of going from -1 to +1, that should be 68. Notice what we got. It is not 68. What is it? The probability turned out to be the probability of being between -1, and I'm going to use a little notation that you're not going to know for 5 seconds. We'll bring it back in 1 second. And I'll explain it 1 second. I'm putting a z there, though. That might look a little confusing. But the probability of being between -1 and +1 is 0. Let me scoot this to the side. 0.68268. So why is it called the rule of 68, 95, 99.7? I'll just call it 0.7. Why is it called the rule of 68, 95, 99.7? Well, they rounded. It depends on how much accuracy you need. So in another class, they might call it the rule of 68.3 instead of the rule of 68. So you might be saying, Professor Dwork, does that mean you lied to me about the rule of 2 standard deviations down, 2 standard deviations up? Well, yes, it does. Let's go to calculate, and I'm going to do another integration. And I'm going to, instead, my lower bound, I'm going to go from -2 up to +2. And let's see what we get now. Look, it's not 95, is it? The rule of the 2 standard deviations down and up isn't 95. It's 95.449974. So the idea, different classes will give you different numbers. They're just rounding to something that's easy to remember. But back to what we're talking about. We just found out the probability of getting a test score between a 73 and a 97 would happen 68% of the time. Or 68% of your likelihood of if you're an average student, you are 68% likely to be in that grouping. This is used, for example, like in SATs. This is where they set the average SAT score, and they say the average student scores here, and so therefore 68% of the population should fall between this score and that score. And that's kind of how it plays. So this is also how you get to the concept of percentiles, which we're not going to cover in this class, but I'll cover it in like 5 seconds because at least it's something you guys can connect to. A percentile says what percentage of the population falls from here and below. So if you scored a 97, well, then we know from here down is 50%. And then since this is 68, this would be, what did I say, 34. So 50 plus 34 means you would be in the 84th percentile. That's my secret way of writing percentile. Ha ha ha. Anyway, so what a percentile means is it's this exact conversation. It's just saying you are above this many people. You are above this percentage of the population. So if you are in the 99th percentile in reading, like that's what you get, that means you are one of the best readers in your grade or your age. Okay, so that's the big idea. So what are we going to do? What are we going to do if it's not easy? Like, all right, so let's imagine, all right, so again, same problem, same mean, all right, 85. And the standard deviation is still 12, so up 12, down 12, so that's going to give us what, 85 plus 12 makes 97, down 12 makes 73, right? Calculate the probability of a score being somewhere between 75, and 90. Well, I don't have a nice value to plug in there. It's not a 1 and a negative 1, is it? Right? No. And I don't really want to type in this version of the equation with a mean and a standard deviation. That just doesn't sound like fun. So what we're going to do instead is we're going to convert this. Okay, we're going to come up with a way of converting 75 into how many standard deviations away from the mean am I, right? So, and it's really just kind of common sense. So what we need is we're going to figure out how far is 75 away from 85. To get distance, we do subtraction, right? So 75 minus 85, so that is 10 away, and it's a negative 10, and that's okay. That just means it's 10 below the average. Right? Now, how do I convert that into standard deviations? Well, using the logic from up above, right? 73, if we did one standard deviation down, right? We'd be 73 was 80, the distance between 73 and 85 was negative 12, and that's one standard deviation. So I'm saying break that up into groups of 12, right? Because then if 12 divided by 12, that makes negative 1, which was our one standard deviation away. So same idea here. So what we're just going to say is how far away am I? Take that and break it up into the groups of our standard deviation. So this would be negative 10 divided by 12. So what would that be? Well, I'm going to leave it as a fraction, so it'd just be negative 5/6. So what I'm going to do here is instead of writing this as 75, I'm just going to say this is negative 5/6 for my lower bound. My upper bound would be, all right, 90 take away 85 divided by 12. Because 90 is how far away from 85? Well, it is 5 over, and it's divided by 12, so that would be 5/12. So there we go. Now, I can't keep an x in here because the x has the units of our test scores. Now we have converted ourselves to standard deviations. I want to know what's the likelihood of me being between negative 5/6 standard deviations and 5/12 of a standard deviation. So that is typically called a z-score. So we're going to put a z in there instead of an x. And now that's where the z from the previous problem came from. So now what do? Well, we don't actually have to do anything different other than change our bounds. So in our calculator, now if you want to clear this out so you can actually see it filling in, you're absolutely more than welcome. You just turn off the little equal sign, y equals, go back to the equal sign, hit enter. And now when I go back to here, it will redraw the graph without the bounds, and I can calculate it. Or another way that students sometimes would rather do this is just from the main blinky screen. You say, I don't care. I don't need to see the picture. Oops. So what I'm going to do is just press the math button. And do you see the option number 9, function int, fnint? So I can do it there. And here we go. So our bounds are going to go from negative 5/6 up to 5/12. And my function, since I typed it in my y1, I can actually type in vars, go over to y-vars, it's a function, my function y1. And then what was our variable that I used? Well, I used the letter x. So now I want to hit enter. Voila! It has now given us our answer of 0.4592. So what is the probability of us getting a test score between negative 5/6 standard deviations and 5/12 standard deviations? 45.92%, or 0.4592. Okay, that's the big idea. So before we move on, I just want to point out the z-score formula, I gave it to you right here, and we just used it up above. It's just logic. It is the z is your value minus your mean, your average, divided by your standard deviation. Okay, and that's going to take care of us on this video. We're going to do a little bit more practice in the next videos, and we're going to go into some new concepts, but I think this is a good chunk for now. We'll see you in the next one.